Hello and welcome to this video. In this video we're going to continue on with these gas laws, but now we're going to look at how can we visualize them graphically. We've said that a state that a gas is in is defined by its pressure, its volume and its temperature, and these three things are the only things that we can use to define the state of something, okay, or the state of a gas. And so what we can say is that since we know the ideal gas law, that PV equals nRT, and we're going to assume that basically everything is an ideal gas at this point, then we can say that if I have a pressure against volume graph, so pressure in pascals and volume in meters cubed, any individual point on this graph, doesn't matter where it is, will represent a different state that this is in, with a different pressure, a different volume and a different temperature. And we can travel between these points and these states in one of four ways, okay? So not all of these four ways are going to come up. I'm just going to introduce you to them so that if these keywords get thrown out in an exam question, for example, you wouldn't be thrown off by any of these words, so you have the keywords for you to know. So there are four transformations that take place, and we will draw each of them separately. So let's start off with the first one, which is an isochoric change. Now this is just a fancy word for constant volume. Okay, so we're changing the pressure at a constant volume, and we've actually already expressed something with a constant volume. The relationship between pressure and temperature is P over T should be a constant. So that means if I'm increasing the pressure at a constant volume, the only way I can do this is by heating it up. So an isochoric change means that I start at the same volume, let's call it V1, and I start at a pressure P1 and I'm going to end up at a pressure P2. Now I'm going to do this. Now, from what I've been saying, I know that the direction this goes is this way. But it's also possible that I could have started at P2 and then went down and got to P1. This is why we have to make sure that we're drawing arrows on these PV diagrams to know which direction the energy is flowing. Because if I were to first go up, I'm starting at the same volume, I'm increasing the pressure, and I know from this law that this is going to also increase the temperature, which means I'm putting heat into this system. Right? I'm heating it up so that the pressure increases. But if I then did the opposite, I'm starting with a high pressure, I'm going to cool it down, and then I end up with a lower pressure. Hence, I've taken energy out of this system. So both ways will give you the same type of energy, and this is because all of this energy is heat energy. Okay, so we have heat energy transfer for isochoric changes. Now the second type of change, so let me actually put a small one here and let this be, let's say this goes down, and this is step one. Now the second kind of thing that we can get is known as an isobaric change. Now isobaric means constant pressure. We can hold the pressure constant and we can just change the volume and the temperature. And when we change the volume and the temperature, we know that they are directly proportional to each other. And so if I were to stick at one pressure and I want to get to a second volume, if I go this way, I know that I am expanding that thing, which means that the temperature must have increased. And if I am going this way, then I am compressing this gas, so the temperature must have decreased in order for this to happen. Now the key with this is that there will be heat flow in and out of the system, but there will also be an overall work done. Whether this is on or by the gas depends on what direction it's flowing in. If the gas is doing work, that means the gas is exerting energy on the boundaries of this. Now, if we're going to expand the volume, it means we're pushing out, and so we are going to exert energy on the boundaries. So if we go this way, this means that work is doing by the system, and if we were to go the other way, this means that work is being done on the system, because this is then the boundaries are then pushing the gas inwards, so they end up compressing it. And so the energy here, although we will have heat transfer, it's heat transfer and work done. Okay, so when we have these two, we have two types of energy that are being transferred. Now we've looked at heat transfer and we know how to quantify that. We just look at either if the temperature is changing or the state is changing, then we use the specific heat capacity or the specific latent heat capacity. We just add up all the energies. But we haven't quite looked at the work done yet. And this is why PV diagrams are important, because if we're going to say that we have a amount of energy transferred, we need to be able to quantify that. And what we find from this is actually the gradient of a PV diagram doesn't really mean much, because if I did pressure divided by volume, I'm most of the time just going to get a constant depending on how I'm changing this. And what we actually find is that only the area underneath this graph is actually going to be a valuable thing to measure in this. So the area underneath means that the work done on a graph is actually the pressure multiplied by a change in volume. So this has to rely on there being a constant pressure. If pressure changes, then we have a slightly different formula for that. But in terms of what you need to know, this is how we calculate the work done. So if I had this change, for example, then this is my amount of work done. Okay, the area underneath it is the amount of work done, and then whether it's going forwards or backwards allows you to then express whether it's on or by the gas. The third type of transformation is an isothermal transformation, and this is where we keep the temperature constant. So we have a constant temperature. Now the graphs for isothermal transformations are slightly different, because this is a pressure versus volume graph. So this is how we can tell that each thing has a different temperature, because if we say we're going to fix the temperature, we then know that pressure and volume are inversely proportional, okay, from the Guy-Lussac law or even the Boyle's law. And so if we know that these are inversely proportional, we have this kind of relationship that P is going to be proportional to 1 over V. So if I'm now going to draw out a isothermal change, it's going to have a reciprocal look. So I'm going to start at P2 V1, and I'm going to end up with a reciprocal graph that's going to end up at some V3 P1. Now everywhere along this graph is a constant temperature. If I then increase the temperature, so let's call this TC for a cold temperature, and then if I increase the temperature, I end up with a higher pressure, and I will follow the same curve, but it will end up being higher because this is TH, which is hot, okay? And again, it doesn't matter if I'm going, or it does matter even, if I'm going forwards or backwards, because if I'm going to go forwards along an isothermal, it means that I have some positive work done because my value of delta V is going to increase. So this is the amount of work done in this section, and then the second isothermal is then going to have a different amount of work done, which would be the larger area. Okay. The final type of transformation is not something that is going to come up often unless you are doing the engineering physics course at the option at the end, in which case you will have to know a little bit extra about these changes, and these are adiabatic changes. And an adiabatic transform means that we have a boundary of the system so that there's no heat transfer with anything outside. If we're going to change in an isothermal in an isothermal change, there is also both work done and heat transfer. Okay, and you would think that surely if you've got heat transfer, you would end up changing temperature. But actually, if you imagine a system where I am, in this case, decreasing the pressure but increasing the volume, that should cool the system down, right? So we have to then have some heat transfer into the system in order to maintain the constant temperature. And the same if we went the opposite way. If we were to then compress this thing so that it got higher pressure, you'd expect more frequent collisions. There's more energy transfer. This is going to heat up. If you then want it to remain at the same temperature, you have to have something that takes an amount of energy out of this. So these isothermal changes will take into account a work done and a heat transfer. Adiabatic changes basically just mean there is no heat transfer. Okay, so we have a boundary on this wall that means that we can't get heat in or out of the system. So this leads to this idea that the total internal energy doesn't change. The internal energy of the system doesn't change. And from this we can then say that what happens if we were to do something where we actually want to do more than one transformation at a time, because we only have 4 different paths that this can take. An adiabatic path is going to look something more along the lines of having a exponential decrease, something like this, and then again we would say either goes forwards, or we could have another adiabatic that's going to go or backwards and then forwards respectively. Okay, so these are all your types of transformations, but then we can make cycles out of these. Now for the most part, cycles are not a very common type question, but we're going to introduce them anyway so that we're fully prepared. So if I then had an example of a cycle, so I can pick any 4 transformations and make it a cycle. I could even do more than 4 if I wanted to, but I'm going to take a common example, and this is basically the example of how a petrol engine works. So I have a pressure in pascals and I have volume in meters cubed, and a petrol engine works by having 2 isothermal changes and 2 isochoric changes. Okay, and what happens is I'm going to say, let me start off at this point here, and then I'm going to get isothermally to this point here, so I end up with this 1/v type relationship, and I get to this point here. Now I'm going to go this way, and we'll see why we're going this way in a second. I'm then going to have an isochoric change, which I'm just going to have a decrease in the volume, decrease in the pressure. So I'm cooling this down. Then I'm going to have my second isothermal, which is going to take me back up to here. And then I have my final isochoric, which is just the connection between these. And now notice how, because of this kind of cycle behavior I have, I've trapped a little bit of area in between. And actually, in this case, the area in between this, so the area enclosed, is the work done by or on the system, depending on the direction of rotation. Okay, so either work done by or work done on. Okay, so it does depend on the direction. We find that this is an engine, so when you have a clockwise cycle, you end up with engines. Now we know engines are doing work, so this means that work is being done by the system to let energy out of this. So engines, we have work done by the system. And if I were to go the opposite way, those of you who are doing engineering physics will find out that if I were to curve this around the opposite way, instead of using the heat energy to transfer energy out of this system, you're actually using energy or taking energy from hot to cold. In the reverse of this, I'm taking energy from the cold to the hot. So I end up with a fridge. It's basically a fridge or a freezer or anything like that. And that means I'm doing work on the system because I'm trying to heat up the system by compressing it or expanding it and so on. So the key points to really take away from this is the fact that we can make these PV diagrams that have these transformations, but the very key point is that the work done is P times delta V, okay, which means you can have positive work done and negative work done. And depending on if it's positive or negative, depends on if you're doing work on or by the system. Usually you can kind of figure it out from the situation that they give you, whether you're going to be transferring energy out of the system or onto the system. But yeah, this is the important point from this video. This is not on your formula sheet, so it is something that you do have to know. And the implications of this, we're going to find out, is that if PV is a unit of energy, that also means that nRT is a unit of energy. So we're going to investigate that more when we look at the kinetic theory of gases.